Hello guys and welcome to another calculus video. In this video we are going to be starting a new series on the channel which I hope can prove to be very interesting. As you can see, I'm here on a random number generator, so I'll go ahead and hit that. We got a 3 and I'll show you why we went ahead and did that. So here you can see I'm on the StackExchange page for the Derlet Integral right here. And the reason that I'm here is because in this series I'm calling it StackExchange Roulette because what I'm going to do is I'm going to start on a well-known integral right here, the Derlet Integral, very, very classic. Everybody knows how to solve this. So what I'm going to do is I'm going to go ahead and go to this related tab. As you can see, I've already clicked on it once. I'm going to go to this first integral that pops up here, whatever it is, that I haven't seen before. And I'm going to go ahead and click on it, and I'm going to do that, repeat that the number of times that the random number generator gave me. So 3 times, we're going to go ahead and click on this first integral right here. Then we'll go ahead and go to this first one, click one more time. And then to find our third integral, we're going to click on this first related integral right here. Alright, so this is our integral right here. We have the integral from negative infinity to infinity of x squared over cos x dx. So there's actually a few ways to tackle this. As you can see, they're doing some very, very nasty contour integration stuff right here, but that's not what we're going to get into because this is an integral that I've solved in the past, but it's always nice to kind of go back and do these solutions again. So we have our integral is the integral from negative infinity to infinity of x squared over cos x dx. So we'll rewrite this as 2 times the integral from negative infinity to infinity of x squared, or not negative, we want positive infinity, or 0 to infinity now because that's going to make things easier for us. X squared over cos x dx. And now 2 times the integral from 0 to infinity. And actually we'll put a 4 up here because of the definition of cos. And then we're going to put x squared and we're going to multiply by e to the negative x on the top and bottom. And on the bottom we'll end up with 1 plus e to the negative 2x dx. Alright, and now we're going to apply the power series right here. 1 over 1 plus u equals the sum of u to the n from 0 to infinity for the absolute value of u less than or equal to 1, or less than 1, or equal to 1 actually. No, that doesn't work at all. So we're going to have 4 times the integral from 0 to infinity of x squared e to the negative x times the sum from n equals 0 to infinity of negative 1 to the n e to the negative 2nx dx. Now we're going to go ahead and apply Fubini's theorem here. And we are allowed to apply Fubini's theorem right here because if you go ahead and throw in absolute value bars in here, we actually end up with the integral from 0 to infinity of x squared over hyperbolic sine of x, which does converge as well. So we can go ahead and interchange the integration here, and we'll end up with 4 times the sum from n equals 0 to infinity of negative 1 to the n times the integral from 0 to infinity of x squared e to the negative 2n plus 1 x dx. Now we'll just go ahead and substitute u equals 2n plus 1 x, and then after we calculate our differential, we're going to end up dividing by 2n plus 1 cubed. So we'll get 4 times the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1 cubed, times the integral from 0 to infinity of u squared e to the negative, or e to the negative u du. Now this is just gamma of 3, which equals 2. So we'll end up with 8 times the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 cubed. Now this is a very, 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 very common integral, or sum that you'll see in a lot of places. So I'll just go ahead and substitute in the value of it, which is pretty well known. It's pi cubed over 32. I actually have a whole video on 3 separate methods on how to evaluate this summation if you want to see it. And so overall our answer is going to be pi cubed over 4. And the great thing is, now that I've solved this problem, I can actually just go ahead and check on that StackExchange page to see if I got the right answer. So let's just go ahead right here. Yep, pi cubed over 4. All right, so now I'm going to go ahead and throw another random number generator here, 8. And we'll just go ahead and keep going like this. I'm going to go with integrals that I haven't seen yet. So this one, actually, we already clicked on earlier. So I'm not going to go ahead and click on this one because, as you can see, it's already blue because we clicked on both of these earlier. So we're going to go with this third one right here. So that's 1, 2. I believe that's an integral, yeah. We already did this one, so we'll do this. 3, 4, I don't think this is an integral. 5, 6, 7. We already clicked on this one. This one, 8. Okay. Integral from 0 to infinity of log 1 plus x squared over x squared using contour integration. Now, I'm not going to go ahead and start by using contour integration just because I'm not sure it is actually the best method to solve this. So I'm going to start with probably a different method, and then we might circle back and try contour integration as well. So let's go ahead and just start by using Finemans Trick here. So we have integral from 0 to infinity. Let's go ahead and switch back to white. Integral from 0 to infinity, ln 1 plus vx squared over x squared dx. And this is a parameterized integral with respect to v. Now I of 1 equals our original integral I, and I of 0 equals 0. So I prime of v is going to equal the integral from 0 to infinity. Now from chain rule, the x squareds cancel, so we just get 1 over 1 plus vx squared dx. Then we substitute v root v times x equals some variable u, and then we'll get 1 over square root v times the integral from 0 to infinity of 1 over 1 plus u squared du. This just came from calculating the differential. And so overall, we're going to get that I prime of v equals pi over 2 square root v, which means that now we're going to integrate both sides from, as you can see here, we have this I of 1 and I of 0, so we're just going to integrate from 0 to 1 here, 0 to 1 dv. So we end up with I, because we end up with I of 1 minus I of 0, which is just I, equals pi over 2 times the integral from 0 to 1 of v to the negative 1 half dv, which equals pi. And that should be the answer right there. Now, the reason I was able to see this so quickly is just whenever you have sort of x squared on the top and x squared in some function, when you place a parameter next to that x squared, it's going to differentiate out super easily. So that's just something that I know off the top of my head. So let's go ahead and actually let's check the answer, and then let's see if we can actually solve it using contour integration. So yeah, this is just going to be pi as well. So let's go ahead and try and use the contour integration here. So basically, let's analyze this function real quick. We have our function natural log of 1 plus z squared over z squared. And actually, I should not be writing natural log here. I should be just writing log. Now, notice that log 1 plus z squared, if we expand it as a power series, is going to be z squared minus z to the 4th over 2 plus some other terms, which means that we don't actually have a pole at 0, so we don't have to worry about that. Now, we do have to worry about is the branch cut right here. So I don't want to actually split this up into two separate natural logarithms yet, But what I do want to do is actually let's go ahead and do that. Let's write log 1 plus z squared equals log I plus or 1 plus let's do it in this format. Let's do it 1 minus iz plus log 1 plus iz. And this is valid, I believe, when the imaginary part of z is greater than or equal to 0. I'm not entirely certain about that, but we can go ahead and check when we go ahead and do our integration. So in terms of actually solving this integral, first of all, let's look at our original integral that we were looking for right here. From 0 to infinity, we can rewrite our integral I equals 1/2 integral from negative infinity to infinity of ln 1 plus x squared over x squared dx. And so, as you can see, we're going to have to we can go over the entire real line, and so that gives us a lot of ideas here. So looking at these two natural logarithms here, we're going to go ahead and figure out where the branch cuts are. So in general, what I'm going to say is I'm going to choose that log of 1 minus iz, or sorry, I should write arg of 1 minus iz is going to be between negative pi and pi. This is the principal branch of the natural logarithm as well, so that makes it really easily. I believe I should have lowercase ones right here. So I'm going to choose these as my branch cuts because I know that that usually works out very nicely. And so what this means is that whenever we have this natural logarithm and we're choosing the argument to be between negative pi and pi, that means that our branch cut is going to be whenever the input of the natural logarithm is a negative real number. So that means 1 minus iz equals negative alpha, where alpha is a real number. So if we go ahead and solve for z here, we're going to find that negative iz equals negative alpha minus 1, or z equals negative I times alpha plus 1. And notice that if alpha is, again, a positive real number, then this is all going to be in the lower half plane for 1 minus iz. And for 1 plus iz here, we're going to also set this equal to negative alpha. It's almost the exact same thing, except we're going to get negative alpha minus 1. And we're going to get z equals I times alpha plus 1. And the importance of this is that this happens now, again, alpha is positive and real. Our branch cut is going to be starting at the point z equals I and running up from I to infinity. So what this means is if we go ahead and set up our contour integral, the path that we're going to choose here, this is our real axis integral, which is what we're solving for here. So we'll just go ahead and put this in a clockwise oriented manner. Then we're going to go up in the upper half plane. The trouble here is we have a branch point at z equals I, as I just talked about. And then again, this is going to be running all the way up to infinity. And also we have this branch point at negative I and running all the way down to negative I infinity. So what we need to do is cut off our contour right here. And we need to go down and around the branch point and then back up. So this should work out pretty nicely for us. Basically what we're going to need to do is there's actually no residues anywhere at all. So all the contributions are going to come from these integrals right here. So let's go ahead and erase this right here. We don't need to worry about that. So we're going to say that the contour integral of f of z dz equals 0, first of all. And this equals our integral over r, which is our original integral I, plus our integral over gamma, which I can already tell you is going to go to 0, simply because we have basically ln z over z squared as z goes to infinity, and then we have this infinite circle of radius r, but that only contributes one component of z, so we still have natural log of r over r as r goes to infinity, just goes to 0 as well. So we don't need to worry about that. Then we have plus, I'll call this I1 and I2 right here. So plus integral over I1 plus our integral over I2. And notice that as we let these two sort of integrals go towards this branch cut right here, as they become closer and closer, basically everything in I1 and I2 is going to become exactly the same. They're just running in opposite directions. So almost everything is going to cancel in that integral, and they're going to be exactly the same. There's just one difference, and that's the contribution from this natural logarithm is going to change because we're going around essentially from this natural logarithm's perspective, we're actually going a full circle around when we go from I1 to I2. So notice if we plug in some point in the positive half plane here, we're going to get a value. Let's say we plug in the point right here. In terms of log 1 plus iz, this is actually going to be somewhere over here, I believe, in the complex plane, which means we're approaching the argument equaling pi. And that means on the other side here, we're going to be approaching the argument equaling negative pi. So essentially what this means, also the contribution from this natural logarithm is going to go to 0 as well. So what this means is essentially when we have these two integrals added together, we're going to have integral from 1, or sorry, I should write from I to I infinity. Now this is the left integral right here. This is I2. Integral from I to I infinity. Now remember the argument is going to be negative pi here. So essentially we can write negative I pi plus ln of absolute value of 1 plus I z over z squared dz. And this other integral I1 is just going to be the integral from I infinity to I of plus I pi plus natural log of absolute value of 1 plus iz all over z squared. And again, I have done some little hand waving here, and I have sort of made some things disappear and not fully explain where they went, but I just want to keep this video relatively succinct because I don't want to be explaining everything. I do have several videos where I go in depth into how these two branches sort of cancel each other out. And so as you can see right here, since one of them is the integral from I to I infinity and one of them is the integral from I infinity to I, they're essentially negative each other. So we can go ahead and cancel out this part with this part. And all that we're going to have right here is the contributions from these because these also alternate in sign. So essentially we're going to have integral from I to I infinity of minus I pi over z squared, and then we're going to also subtract I pi again. So minus 2 pi I. We'll write that as minus 2 pi I over z squared. And usually in this case, I would actually go ahead and substitute z equals iv, because that just makes everything a little bit easier. But in this case, this is a completely nice and analytic function pretty much everywhere in the complex plane, so we can just integrate normally, which actually does work in the complex plane as well. So this is going to be 2 pi I over z, evaluated at I infinity and at I. So obviously, at I infinity, this is just going to disappear, and we're just going to end up subtracting 2 pi I over I. So that's just going to end up being negative 2 pi. So going back right here, this was the value of I1 plus I2, so this means our integral over R equals 2 pi, because this was all equal to 0. And this means that our integral I just equals pi. Alright, that was a pretty fun problem right there. I really hope you guys enjoyed this sort of quick contour integration session, as well as the Finemans Trick section, and of course our original problem that we got, which was a nice little hyperbolic cotangent problem. I'm not sure whether this series will do very well or not, but I'm excited to see what you guys think, so please give me some feedback down in the comments as to whether you want to see more videos like this, or you want to see some more normal videos where I go in depth on a more project style problem. So, anyways, I hope you guys enjoyed this video. I really think that it was a lot of fun, so again, please let me know what you think. Feel free to join my Discord if you want to talk with me, and yeah, thanks for watching. I'll see you next time, and bye.